Hello everyone, welcome to my channel. Today we will learn about the design of built-up column. So for today's numerical, this one is the given. Design a built-up column 8 meter long to carry a factor load of 1700 kilonewton. The column is restrained in position but not in rotation at both ends. This is the condition given and condition given. Design the column section using two channels. We have to use two channels. Place face to face and suitable lacing with welded connection. We have to design it by welded connection and use FY 250 MPa. So let's see how it's we have to calculate. So first step, as we have followed in previous numerical also, and from the given load condition and end condition we have to calculate first selection of section. So in the first step we have to assume design compressive stresses, that is FCD, as 150 MPa. We can take it 150 to 200. We are assuming 150 MPa. Then factor load we have given 1700. So from this formula given in clause number 7.1.2 IS 800, area required we have to calculate. So load upon compressive stress. So 1700 is our factored load. So divided by 150 FCD. So area required we have calculated. So after that we have to select an channel section from steel table such that its area should be greater than the area required. So we have selected ISLC 400. You can see in the steel table also. So you can see in this steel table, this is the channel section, and I have taken this ISLC 400. You can see here the sectional area 58.25, it is centimeter square, so it is around 5825 millimeter square. So if you multiply by it 2, so we'll get the total area is just greater than this our area required. So that's why we have selected ISLC 400. Also we have to write its all properties like area, width of flange, thickness of web, RXX, RYY, thickness of flange, CYY, G 60 mm, that is IXX, IYY and IZZ. All the properties we have to write. We have to use this in further process. So in the second step we have to determine effective slenderness ratio, that is lambda E, and effective length from given end condition. So end condition is that the restraint in position but not in rotation at both ends. It is given in our numerical. So from table 11 IS 800 we can get the effective length, that is scale. From the table 11 we have determined that effective length is equal to 1L. So our length is given, length of column, that is 8 meter, so it is 8000 mm. Similarly we have to determine slenderness ratio, that is KL upon R maximum, as we already written that RXX and RYY values. So maximum value we have to take R max, it is 155 mm, so it comes as 51.61. After that the effective slenderness ratio we can calculate through this formula. The clause number 7.6.1.5, page number 48 in IS 800, it is clearly mentioned that the slenderness ratio for channel section, the if that section connected with the lacing, then we can take the slenderness ratio is 1.0 times of the effective slenderness ratio. So that's why it is calculated 54.19. In the next step, we have to design compressive stress, that is FCD. Earlier in first step we have assumed that FCD 150. Now we have to check whether that actual FCD from the the effective slenderness ratio, how much it is calculated. So from table 10, buckling class for channel section is class C. It is clearly mentioned in the IS 800. If the channel section is given, its buckling class is C for all channel sections. So to determine actual FCD with the buckling class C, the table number 9C, page number 48, we have the number of values for different KL by R ratios. So our we have just calculated that effective slenderness ratio 54.19. so through that one we can calculate from the interpolation method the what is the FCD for this KL upon R ratio. So from table number 9C, we can write down like this one: KL upon R value, the our value 54, that is in between the 50 to 60. In table number C, you can see the table number 9C, the FCD's value. We have given that yield stress, that is 250. So for 250 and KL by R ratio we have calculated as 54. So it is between 50 and 60. So we can write down the FCD for 50, it is 183, and for 60 it is 168. So you can see here I have written this. So the simple formula, that is the interpolation method, we can calculate the FCD, it is 174. So by using this FCD we can calculate the actual design compressive strength, that is PD, by using gross area. So this is the formula: PD equal to AG into FCD divided by 1000. So it is calculated as 2034 kilonewton, and which is greater than the our factored load, that is 1700. So we can say it is the safe channel. This is our next step, step number 5, spacing of channel. From this step we are going to design of lacing and all these things and connections. So for this one we can take the IYY is equal to IZZ. So as mentioned in the numerical, channel section place at face to face. So from this formula, 2 into IYY plus area of section into S by 2, S is nothing but our spacing between the two channels, CYY square equal to, that is IZZ, 2, it is written as 2 channel section. So by putting all this value, this IYY, CYY, IZZ, these all value we have already calculated from the steel table, all channel section properties. So through which the spacing between two channels, you can see in this diagram, we have calculated 328. So we can write down it, round up, that is 330 mm. Next step is we are going to now design of lacing flat. Actually what is lacing flat? It is the simple flat section, steel section, which is we have to connect it to these two channels. This you can see, this is the top view and this is the front view. These the two channels we can connect it through this lacing flat. This is nothing but the lacing flat. We have to calculate its thickness and width and length according to the angle. So this is our first step, design of lacing flat. So to design the lacing of flat, we have to first assume the angle of this lacing we have to connect it. So theta we can assume 45 to 60 degree. So we are assuming 45 degree. After that we have to calculate spacing of lacing. You can see in this diagram, this is the A1, that is the spacing between two lacing. So for this through this formula we can calculate A1, that is equal to 2 into S minus G which is already calculated into cot theta. So by putting all this value, we will get the spacing between lacing flat. After that, we have to calculate the slenderness ratio of lacing flat. It is given in clause 7.6.5.1 IS 800 page number 50. This formula it is given, the slenderness ratio, it is spacing of lacing divided by RYY, that is minimum. So it is given that 21.8, 28.1, and it is calculated as 14.94. It is also mentioned in this clause it should be the less than the 0.7 times of spacing of lacing. So it is all calculated as less from this, so it is okay. In next step, the transverse shear in lacing flat we have to calculate. It is indicated by Vt. It is also given in clause number 7.6.6.1, same page number 50. It is clearly mentioned that the 2.5% of axial force in the member, and it is equally divided into all lacing parallel planes. So that's why the shearing transverse is equal to 2.5% of factored load. So it is given as 42.5 kilonewton. So after the calculation of transverse shears, we have to calculate the compressive force in lacing flat. It is we can indicate the C. So it is also given in clause number 7.6.6.1 from page number 50 IS 800. The transverse shear divided by number of lacing into cosec theta. We have assumed the theta 45 degree, and n is the 2 for single lacing on both face of channel. Sometimes we can, it is taken, this is our single lacing, sometimes it is double lacing also provided, such type. So our lacing has been considered as single lacing, so that's why it is number is 2. So through which we have calculated the compressive force in lacing flat. After that, we have to calculate the width of lacing flat B. It is also given in clause number 7.6.2. The width of lacing flat is the 3 times of diameter of bolt. So for this we can assume here 16 mm diameter of bolt to determine the width of flat. It is just like this is the flat. So this is the our width, and this is nothing but the thickness. So this such type of we can calculate the width of flat. It is calculated 48 mm, so we round up it 50 mm. So after the width of flat calculation, we can determine, so after the width calculation of flat, we can determine the thickness of flat, that is T. Again, it is given in IS code clause number 7.6.3 page number 50 IS 800. T should not be less than the 1/40th of effective length of flat, and length of flat we have already calculated in previous step. So thickness, it is 1/14th of the length of lacing flat. So 140 is the length cosec 45, so it is round up 15 mm we have calculated. So these two things we have already calculated. This is the length, width and thickness. So the design of lacing flat we have completed. So for lacing of flat, we have also calculate the minimum radius of gyration, that is R. So it can be calculated through this formula, T divided by under root 12. So it is calculated as 4.33 mm. So from this radius of gyration we can calculate the slenderness ratio of lacing flat. It is also given in clause number 7.6.6.3 page number 50 from IS 800. The slenderness ratio L by R, 0.7 into spacing of lacing cosec theta divided by radius of gyration. So through this formula, just put the values, we will get the slenderness ratio, that is 96.02, And in the clause number 7.6.63, it is clearly mentioned that the slenderness ratio should not be greater than 145. So calculated is less than that one, so it is okay. So after the calculation of thickness, width, length of lacing flat, we have to determine design compressive strength of flat, that is PD. We have earlier calculated that effective slenderness ratio also. So from that one, 96.02, and buckling class also we have for channel section, it is C. So from table number 9C again we have to calculate FCD for this slenderness ratio of lacing flat. So again from that table number earlier we have also seen we have to determine this actual FCD. So it is calculated as 112 through interpolation method from these values, and the design compressive strength, that is AG into FCD. So this area is nothing but your lacing flat, so width into thickness. So it is calculated as 84 kilonewton, which is greater than our earlier calculated strength of lacing flat, so it is okay. So after compressive strength we have to determine that the tensile strength of lacing flat, that is TDN. Again in tensile tension member design we have already seen that the three types of their calculations of the tensile strength, that is it is due to yielding, and second one is the rupture. So this is the formula given: TDG equal to AG Fy upon gamma MO. Gamma MO and gamma M1 we can taken from the table number 5 IS 800. So again area, it is the width into thickness into Fy 250 divided by gamma MO, it is calculated this one. Again similar, it is due to the rupture tensile strength, that is 0.9 BT Fy upon gamma M1. This formula already given in IS code. So it is 1300 135. Again it is greater than our calculated strength of lacing flat 31, hence it is okay. So after the compressive strength and tensile strength of lacing flat, it is completed the design of lacing flat. So after that the connection, we have already designed the channel section, lacing flat, and now it is time to for connection design. So for the connection design, in the numerical it is given that we have to connect connection completed through the welding connection. So assume size of weld 5 mm. We have to determine strength of weld through this formula: 0.7 into S into Fe upon root 3 into gamma mw for the weld. Again it is taken from the table number 5 IS 800, it is 1.5. so the strength of weld calculated 552 Newton per meter. It is unit per meter strength, unit per meter length. So the length of weld required, length of weld we can calculate the strength of weld divided by strength of lacing flat divided by strength of weld. So it is calculated as a C we have earlier calculated, so it is 31.82 divided by this one, the strength of weld. So it comes under calculated as 57.64 mm. Again for welding provided in both way, so that's why the total length of the provided weld is 2 times of the width and 2 times of the second width of the lacing flat. So it is the width is 50, again it is 50, so it is calculated 200 mm. So finally we can write down the provide 5 mm thickness, 5 mm size of weld for 200 mm length to the lacing flat and the channel section connection. So this is how the our built up column we can design with the lacing flat and the welded connection. If any query you can write in the comment box. Thank you.